This is the example for acceleration. This is using the velocity diagram that we used as the example earlier. So in this situation, link BA is rotating at 40 radians per second in a clockwise direction. Again, we start at point A. Our known point, we need to establish where B is traveling. I have, as per my notes, we have two accelerations. We have a tangential acceleration and a centripetal acceleration. I'm trying to find point B, so I need to draw my accelerations at point B. Okay, if I'm trying to find point B, I draw them at point B. A tangential of BA is equal to 0 because this thing is not accelerating, it's going at a constant rotational speed. It will, however, have a centripetal acceleration, AC of B relative to A. Now I can calculate those. AC of BA is equal to V squared BA over radius BA. From our velocity diagram, we get the velocity information, which is 12 squared over 0.3, 480 meters per second squared. What I get people to do for a start is to draw that. There's my little vector. It's a vector traveling down that way. We know it, we label it as we head up there, AC of BA. Arrow points to the first letter. B is at that end, A is at that end. Notice that the lettering is different there than they are up here. They're the opposite way around. B's at the top, here B's at the bottom. This is the reason that sketching it's quite good. So now we'll draw that one. Here's my angle. Come onto my page and draw that through. We now need to scale off here 480. And we'll label it AC, BA, arrows going downwards, same as my little sketch. Therefore B is at the bottom and A is at the top. Okay, next point I need to find is point C. I need the acceleration of C relative to something and the acceleration of C relative to something else. As per last time, C is joined to B, C is also constrained by A. So there is a CB and a CA part that I'm looking for. CB is a link, therefore it will have two parts, AC and AT. In all of these ones I can calculate AC from using the velocity diagram, but the tangential one will be unknown in each case. What I need to do is cross my lines and establish that point. AC is equal to V squared over R. From my velocity diagram we said that this was 6.35 squared over 0.9, which is 44.8 meters per second squared. Okay, since CB is a link, C will have two accelerations. It will have a tangential acceleration, AT, CB, and it will also have a centripetal acceleration, AC of CB. Again, I'm finding C, I draw the accelerations at C. So this is my acceleration. I can draw my little arrow in, AC, CB, arrow points to C, B will be at that end. So now I can take this vector and draw it onto here because I know where B is. So I can take my little vector, it is in line with that, transfer that down, put my line through B. I know it's going away from B, so it's going to be going that way, A, C, B, C, B, C, B. This is only part of the acceleration, and we know that it's also 44.8 long. Something about that long. Now I can put on my tangential velocity. So at 90 degrees to that, 90 degrees to this one, and here, I need to draw through this point. That will be my tangential velocity. Now I'm not quite sure which way it's going yet. I need to find something to cross that line with. The other one I now know is A of CA, acceleration of C relative to A. It's not a link, it only has one part to it. So in here, C, A is in here. My velocity of this point can only be horizontal, therefore my acceleration can only be horizontal. Now it's not centripetal or tangential, because it's not a link, it is just the acceleration of CA, must be horizontal. So it'll be a vector passing through C and A. Here's A, so therefore horizontal line through there, where those two lines I've just drawn across must be point C. So on my diagram, this line is the total acceleration of C relative to B. This one here must be the tangential velocity of CB. Now this point down here isn't actually a real point. I have to add this part of the vector and that part of the vector together to get the total. So this is not a real point on the diagram. So these become light lines or dotted lines. Okay, and that's my acceleration diagram. I now want to know the acceleration of CA. CA is the length of this line here. I can get that and determine that as 165 meters per second squared by measuring that. So that's my acceleration of CA. CA, arrow goes to the first letter, therefore this is accelerating that way. So on my little diagram, I can now put an arrow there. Don't put it there to start with, only put it there once you know it from the diagram. The other one we want to know is the angular acceleration of BC. So I want to know the angular acceleration of BC. The equation we had from last year, A is equal to alpha r. These are the tangential accelerations that it's actually referring to. So this will be AT of BC over radius BC. AT of BC, that's this line here. If you scale that off, that will come to 420 meters per second squared. So this is equal to 420 over 0.9, which gives me 467 radians per second squared as my rotational acceleration. The last part we need to establish is the acceleration of G, which is the acceleration of the center of the mass. We need that to be able to work out inertia forces, which we'll deal with later in the course. So we want to find out what is the absolute acceleration of G. So it'd be G relative to A in this case. As per the velocity diagram, G is 1/3 of the way along BC. So as before, here is my diagram. I am 1/3 of the way along between BC. So take that, measure that, work out where 1/3 is. I'll do it approximately, just be here. So this is point G, and I'm looking for the acceleration of GA, G relative to point A. Now again, this is not a link, it does not have centripetal and tangential parts. This is just the acceleration of G relative to A. Arrow is going to point to the first letter. So G will be accelerating down that way. Take that back onto here if we need to. We can put that down here. G is accelerating this way. Acceleration of G A. To find it, measure that length. This length here we can measure at 350 meters per second squared. Acceleration of G A.